Right. Hello, everybody. My name is David Ratchkov, and I wanted to quickly introduce some of the work we have been doing at CDX. I have the pleasure of introducing some of the slides, but really we have many more contributors, and I specifically want to acknowledge Tony and Jawad. They're not able to make it today. Actually, only Jawad is not able to make it. Here's Tony. Thank you for your help on this. And James is going to cover some of the slides. I currently lead the CDX work stream, and I wanted to quickly go to what we're going to cover today. I wanted to introduce you all to what CDX does, what we're working on, and what our goals are. I'm going to briefly cover some of the work we have done with regards to chiplet models. Why do we need them, and what we are doing with chiplet models, and give you some idea of the work that we have done. Then I'm going to hand it off to James, who is going to help us explain the CDXML, what it is, what we use it for. And last, I'm going to conclude with call to action and some concluding remarks. CDX is a work stream under ODSA sub-project. Our focus is on electrical, mechanical, and thermal exchange standards, and really anything that's related to excuse me, related to chiplets and chiplet integration in the context of multi-chiplet modules. This includes both the 2.5D and 3D contexts. We strive to enable the foundation for an open marketplace, similar to what's being done for silicon IPs to today, and similar to the way the component businesses operate. The way we achieve that, we identify the needs, and we develop new guidance and standards to enable exchange of design automation data. And really, that's for the purpose of chip designers to be able to freely buy modules and integrate them all together seamlessly. And definitely for high volume manufacturing, that's a very, very important aspect that needs to be considered. One of the work that we have done is we wrote a white paper. It's part it's the first part of a two-part white papers. It has the mouthful name of Proposed Standardization of Chiplet Models for Heterogeneous Integration. I wanted here to thank all authors, and I'm glad you're using your phones to scan the paper. Thank you. I'm glad that QR code is working. Really, in that paper, what we covered is what models, from the point of view of chiplet vendors, what models they would need to be providing to chiplet integrators so that they can be successful in their integration. We have provided a list of models with some recommendations which are optional, which must be provided in all cases. I wanted to briefly show you a quick table. And I want to thank Tony for that table, great table, Tony, thank you. That covers just briefly what models we have considered. We started with thermals, we looked at physical, mechanical, and I/O models that are needed. We looked at behavioral models. Power is also a big aspect. Right, what models we have to exchange both for power implementation and power analysis. We looked at SI, PI, those are big topics when we're talking about chiplets on the same substrates. Electrical rules, and one thing that we identified in some of the electrical rules as gaps is where CDXML comes in, and James is going to cover how CDXML fills the gaps. Test is a big topic, and as such a big topic, you can see that there's quite a few standards that are mentioned that cover all different aspects of DFT that are important. security, and lastly but not least, any documentation and guidelines that chiplet vendors need to provide to chiplet integrators in order to achieve successful integration. Basically, the guidelines would be anything that we could not put in data in machine readable file formats. I think with this, I want to hand it off to James, who is going to walk us through CDXML.
All right. Thank you, David. We talk about the chiplet model, and now let's look at the challenges that facing the chiplet model. Here, the design of chiplet-based systems require the chiplet data for the following reasons. First is like integration of multi-chips with the different IP nodes and technologies. Obviously, all it's going to be expecting coming from very different vendors. Each of them will having like a very different data set and norm and things like that. So, and then there's a die-to-die interface. You hear quite a number of them, right? Such as a bunch of wires, UCIe, and so on. So each of them we could expecting vendor will be supporting one in another both. So we have to know, right, what are there in order to put these things together. Same as for the power distributions. We need to learn about, right, each power usage on each rate in order to put them together when we do a chiplet-based design systems. Same as the thermal dissipation, each chiplet will have their own kind of like different dissipation when put into the systems. We will require some sort of the data and in order to do the overall system thermal dissipation properly. Same as simulation and verification. So at some stage you have to do that. It will require the data again from many different chiplets put together so you can run a proper simulation and then do a verification, right? Also, built-in self-test is very important since this is chiplet-based design. You're going to either, like Pabi has mentioned earlier, you either to put many different diodes together coming from different vendors. Each of them, you might need to test through them, make sure they operate properly in this kind of heterogeneous design in order to make sure that it's usable in the system level. Same as the overall system level testing, you require again the chiplet data in order to do the overall testings. Also important is the operation condition of chiplets. Near this thing, you find this information, especially in the data sheet and things like that. You will see like there's certain chip that operate at a certain temperature on a certain voltages. So when you put different chiplets together, you need to watch out for that so that you don't kind of run into certain thermal or temperature that might work for one chiplet but might not work for another. And lastly, now there are sensitivity and robustness of the chiplets, such as ESD. I think this has been one of the areas has been underside in many ways. And recently we have been talking in the CDX workstream as well that a lot of this information today are available only in the PDF format. So there are not really many tools like even the EDAs. I think I focus a lot around this area. That's something I think it become even more important in the chiplet design, so that because every die or chiplet, they probably have a certain kind of sensitivity, how you're going to handle them one versus another, so that when you again put this thing together, you want to make sure that is one destroy because there's certain most sensitive chiplet is used inside the system. All right, let's look at what we have been doing at the CDS. We facing with these challenges, so we come up with a proper solution called the CDXML, which is stand for the Chiplet Data Exchange Markup Language. This is adapted the JEP open source model from the G group. So some of us are the team member originally from G group. We are now in the CDX. So we work together to trying to define a standardized XML format with a schema. And this data contain the following information of chiplets. On the top level, we have the mechanical informations that describe all the mechanical related information. We will look into a bit more details in the next few slides. We also have I/O definitions of the chiplets, electrical, and assembly information as well, and the die-to-die interfaces, as well as the power and the thermal information of the chiplets. All these things will be describing in the schema, and the data are present in the well-formed XML format, so that we have data that required to solve the challenges that we are facing in the chiplet-based design system that we described earlier. Okay. All right, so today on the high level, the CDXML format, we have 4 main sections: the mechanical, which describe the XYZ, soldering time, material property. We also have the I/O information that describe all the pin locations, the functionalities, mode operations, the EC, absolute max values, all every at the pin level. We also have electrical information that describe overall electrical information. You will see some overlapping at the electrical level and the I/O level. Such as like the absolute maximum rating, the operating conditions. So, and lastly, we also have the assembly information here that describe the recommended information rules by the chiplet supplier that to help to put the chip together, such as coefficient, thermal expansion, the YANS modulus, uniform profile, and clearance, and etc. So, let's look at next slide. So let's look at some example. On the left, you will see the schema that has been defined on the top section. They're kind of like the common properties of the chiplet, such as like the ID, MPN, which stands for the manufacturing part number, as well as the ordering part number. And we also have the kind of like the orders, the company information. And then below, you can see starting the first section, which is the mechanical. Here you can have a surface mount, compatible or not, orientations, and then you have the width, which in the width you can kind of define the sub-property of the min-max. On the right, you can see an example of the BQ27426, which is a PMIC from Texas Instruments. It's one of the chip we use in the past. We kind of using the chip model in the chiplet format, which work in many areas since there are many common commodities. And you can see like there is a width, length, and also the thickness that's described like mean, typical, max. As you see, that I think the XML on the left there, the schema, right? There's a minimum occurrence equals to 0. I will highlight there, so that's kind of tell you it could be optional. So I think that's kind of define like a flexibility. I think I have in this schema to provide some sort of standard. And lastly, let's look at some example that we have used in the past at the G group when we develop a chiplet-based system in an active interposer. So at the top, you can see that when we input the CDXML, or it used to be JEF, and then when we do a chiplet selection, placements, to DFM checks, design capture, XLV routing, all the way to package design, and XLT, right? We will use this CDXML data and to generate output on the right. All right, this is my last slide. I just want to highlight to you guys that there's a URL GitHub which we publish all this information, schema, XML example. Please feel free to scan the QR code and hope you guys can contribute. All right, thank you. I hand back to David.
Thank you very much, James. One last slide. Participation in CDX comes from a wide range of of industry players, and also individuals which span wide set of roles, from architects to developers to tool developers to chip designers. So we really need your help, and we would appreciate your help. If you would like to join us and help us out, please do so. We meet on Thursdays at 10 a.m. Pacific. You can find our dial-in info on the OCP calendar. And most importantly, our current work is a SIP integration workflows paper. This is the second part that covers chiplet integration from the point of view of the integrator, right? How do we take those models and what workflows do we apply in order to have successful product? So please, if you want to help us out, please do so, and this way you can find us. I think we're right about on time. Thank you.